So it's very nice to be here with you in a virtual sense. I got very nostalgic when I realized that I wasn't going to be able to be in Paris this time. So I painted this picture from a photograph I took in 2010 or something. And so I'm afraid that Paris has changed a little bit for the worse since then. And I entitled it the last time I saw Paris. And I sincerely hope I will be able to see it again before too long. So this talk is, I would like to start by paraphrasing the quote of Cézanne, which was on the poster. And I would say that one should treat mathematical physics through the annulus, the torus, and a rectangle. And that's what I'll be doing in the course of this talk. So I was trying to understand this T-Tbar deformation of a 2D conformal field theory, and understand how various objects in this conformal field theory should retain their modular invariance properties. And in the course of this work, I realized that the proof that I obtained had nothing to do with the fact that it was a conformal field theory, but in fact it has everything to do with the modular properties, how it applies to all kinds of modular and Jacobi forms of 19th century mathematics. So basically, this talk will be about the T-Tbar deformation of 19th century mathematics. But the way I'm going to proceed is by talking about T-Tbar's deformed conformal field theory and essentially using its properties as a model for more general mathematical objects. So just to give you a flavor of what I'm talking about, there's this well-known identity for the Jacobi theta function evaluated at 0. And I think everybody has seen an identity like this, which of course comes up in the solution of the one-dimensional heat equation. And everybody knows how to prove this using the Poisson sum formula. But what it's basically saying is that the test object is transforming like a modular form of weight 1/2, which means it's not really a modular form because the 1/2 would have to be an integer. In fact, it would have to be an even integer, but it transforms as though it were a modular form of weight 1/2 under the S operation of SO2Z. And the T-Tbar deformation of this object has a parameter here which is beta, and it looks like this. So you see the exponent is modified to something that looks like this. If you take the beta goes to 0 limit, you get back to what we had. And the amazing property of this series is that it's, again, and delta goes to 1 over delta, it transforms in a straightforward way. So I think that if somebody gave you an expression like this, you would be amazed if this property was true, but it is. If you try to prove this, by the way, using the Poisson sum formula, you get into some difficulties because you end up with an integral that you can't do easily. But I'm going to show you a way around this, which is going to be much more general. So I need to spend a little time reminding you about what is the T-Tbar deformation of a 2D QFT. It's a family of non-local field theories with a parameter lambda, and it's a flow such that the way that we flow infinitesimally between these non-local field theories is by, at least heuristically, adding a term to the action proportional to the determinant of the stress tensor, which in 2 dimensions is, of course, a 2x2 matrix. And we can express it like this. And the point is that this is an irrelevant perturbation, so it just affects the theory in the UV, and it induces, if we add it as a perturbation to a conformal field theory, it induces left-right scattering, so it spoils the holomorphic and anti-holomorphic properties. And over the years since Homologikov introduced this in 2004, there have been various ways of understanding why this deformation is, quote, solvable. It's solvable, as pointed out by Homologikov, in certain translational invariant geometries, for example, a cylinder or a torus. You can actually take these 2 points apart, and that leads to the solvability, the fact that this object is then independent of y. It's been shown that it's equivalent to a coupling of the theory to a random flat metric, some kind of 2D gravity. I argued that when you use the conservation of the stress tensor to write the stress tensor as some kind of curl, then the determinant is in fact a total derivative, so the action is in some sense topological. But the point of view that I wish to pose you here is that the T-Tbar deformation is equivalent to a state-dependent change of coordinates. And the way that we see this is that if we just write this product of the 2 stress tensors as the stress tensor times an object which are called delta G, where delta G is this, you see this form here has the form of the response of the action to an infinitesimal change of the metric, because that is just the definition of T. So if we at least proceed in a formal way. If we make an identification like this, then if we use the symmetry and the conservation of the stress tensor here and write that out explicitly, it means that in fact that we can write this change in the metric as though it were coming from a change of coordinates. That is, if we start in flat space, we stay in flat space, and the change in the metric of this form is just equivalent to a diffeomorphism. So that's another reason why this particular deformation is solvable. So the T-Tbar deformation is equivalent to a coordinate change. And now if you integrate that equation up for how the actual coordinates change, you see that you can write the flow of the change of coordinates in terms of a line integral over the stress tensor. So we have this deformed system of coordinates, which I've indicated here. We look at a point X, and we have a fiducial point here, capital X, and we look at the flux of the stress across this line, which in normal quantum field theory terminology, if we choose to quantize on this edge-like curve here, then the change in the time coordinate would be minus the momentum flux across between x and x, and the change in the space coordinate would be the energy flux. And at this point, you probably might want to ask what this means, because on the left-hand side of our equation here, we have a coordinate. On the right-hand side, we have an operator. So how can the change in a coordinate be equal to an operator? Well, it makes some kind of sense in correlation functions and in the path integral, but one would like to put some mathematical meat on these bones a little bit. So I'm going to use the example of a rectangle. I could start with a torus, but it's easier to think first about the case of an R0 by R1 rectangle. And here's our point X, which we take on the boundary. Here's the point we're looking at. But if we take small x all the way across to the other boundary, we see that the change in the R1 coordinates is going to be proportional to the normal stress across a space-like line here, which is the energy. So the system stretches in space proportional to the energy. So we can either think about this in terms of space and imaginary time, or we can think of it in the Euclidean point of view, where R0 and R1 are both spatial coordinates. And from that point of view, we're just talking about stress and strain. And in the light of that, I would like to introduce a little digression here, where Cauchy, Lagrange, Euler, and various other people meet at the Academy. Whether they could have actually met there at the same time, I'm not quite sure, but let's assume that they could. So Cauchy speaks first, and he said, all this talk about stress, why not think of this change of coordinates as the deformation of an elastic solid, for which I have a marvelous theory of stress and strain. And I'm there, and I say, well, yes, Monsieur Cauchy, but this strange T-Tbar solid has an infinite Poisson's ratio. What that means, and I assume that all the French people in the audience know what Poisson's ratio is, but for those of you who don't, if we go back to the rectangle here and imagine that it's a sample of an elastic solid, if you compress it from above, with a normal force, the Poisson's ratio is the amount. It's the ratio of the amount by which it expands in a horizontal sense to the amount by which it compresses in the vertical direction. And the amazing thing, which you can see from our equations here about T-Tbar, right, which is this strange elastic material, is that if you try to compress it from above, it won't compress at all in a vertical direction, but will only expand in a horizontal direction. So I point this out, and he says, well, it's not possible. You're all mad. But then Lagrange picks up and says, but if you look at our equations here, which needs to go back to, if you think of R as a position of a particle in a two-dimensional fluid and lambda as time, then and n is the velocity, these are just the equations of a two-dimensional fluid, with n being the velocity and lambda being the time in the Lagrangian picture of a fluid. And then Euler's there, of course. I don't know that Euler was there, but anyway, I believe he was elected a foreign member of the Academy. And then he says, but in the fixed strain ensemble, this corresponds to my Euler equations, which say that the rate of change of the velocity at a fixed point in the fluid is minus u dot grad u, or n dot grad n. And then there's a visitor from the 20th century, Burgers, who says, but that's my implicit equation too. And I use it as a model for the formation of shocks. So it turns out that if we start with the initial data corresponding to a conformal Hale theory, that is, the force is proportional to the 1 over the distance, which is the Casimir effect, then what happens is that the particles that start from a small r move faster than the ones that have a larger, and they overtake them at some point, and that leads to a hydrodynamic shock. And then the physicists from the 21st century say, aha, Samologikov, this must be a Hagedorn singularity, a maximum temperature. At which point the physicists from the academies say, the older guys say, non, c'est pas possible, you're all mad. Anyway, that's the end of my interlude here, and we should go back to the rectangle. So the nice thing about the rectangle is that we have an explicit formula for the conformal field theory partition function. It was worked out first by these people in 1991, and it's a power which depends on the conformal charge of the Jacobi eta function, and of course we, in a rectangle, we don't have the full SL2Z symmetry, but we do have the symmetry under S. So this modular symmetry under interchanging R1 and R0 is true because eta transforms like a modular form of weight 1/2. Interestingly enough, it also does have a T symmetry, and this is basically, if you now think of R0 as time, and you think of it as real time, that is, you make this ratio, delta is the ratio of the two lengths, and you make it imaginary, then the fact that eta is symmetric under T corresponds to the fact that when you compute this and R0 is imaginary time, you are looking at the overlap of a final state with an initial state, and this property has to be there because of the conservation laws of a conformal Hale theory, and the fact that the right movers do not interact with the left movers. Obviously, this is a property which we expect to be destroyed once we add the T-Tbar deformation. So we don't really need the details of this partition function, mainly the fact that it has an expansion in powers of Q, which we can think of as a spectral decomposition of the partition function in terms of eigenvalues of the energy, which we can think of from the Euclidean point of view as just the stress in the timeline direction. So, And because we're not taking a trace, because we don't have periodic boundary conditions in R0, there's going to be some kind of matrix element here with the boundary state, which you see is the test essentially here. So this spectral decomposition we could write as an integral over some kind of modified density of states rho, which include the matrix elements here. So what we're basically doing here from the elasticity point of view is we're starting off with the fixed strain ensemble in which R0 and R1 are fixed, and we're writing this in terms of some mixed ensemble in which N0 and R1 are fixed. If we were thinking about zero as being a temperature-like direction, we will be going from the canonical ensemble to the micro-canonical ensemble here. Anyway, that's an aside from what I've already said. What we should be able to do to go from the undeformed, in order to add the T-Tbar deformation, all that happens is that we shift the coordinate R1 by an amount proportional to the energy. So we've got to work out something that looks like this here. And it should be that this object is still modular invariant under S. And our reason for asserting this is that the T-Tbar deformation is rotationally invariant, so it should not spoil the modulus symmetry. But of course, if you stare at our expression here, because we have made the R0 direction spatial, because we've made a choice of imaginary time coordinate, our expression here has not obviously appears to be modular invariant, although a clue as to why it ought to be is that if you take an expression here and you at least formally differentiate under the integral, which you shouldn't really do because, of course, rho is the sum of the delta functions. But if you do that, you see that the evolution of the partition function obeys a partial differential equation, which is obviously symmetric under interchange of R0 and R1. But that doesn't mean the solution is. And in fact, because this is not an elliptic operator, it's hard to prove that the solution is unique. Nevertheless, it's true, but how do we make mathematical sense of statements like this? So we have to prove a theorem, and I'll just basically state the theorem. I was going to prove it, but I don't think I'll go through that. So as I say, it's more general than anything coming from a conformal field theory. If we take any function which I call f0, which has an expansion part of q like this, which converges to Q less than 1 and transforms like a modular form of weight K. So this would include all kinds of objects like modular forms and modular functions and all kinds of other interesting objects, including if you add an extra dependence on a variables here, they could be Jacobi theta functions or more generally Jacobi forms. Then if you find the deformation like this continues to preserve this symmetry here. So the main thing here is that the exponent here gets replaced by all these square roots. So instead of having a Fourier decomposition in powers of Q with an integer power spectrum, we get this kind of irrational powers here. So just some notes. It's not necessarily a conformal field theory object. We obviously lose the symmetry on the T, that is the periodicity in delta because of these square roots, but it's replaced by something more interesting. If the n equals 0 term here, if delta is negative, that there is a singularity in one side or another of this equation, which means that the series does not converge, but the way in which it diverges is going to be, the way in which it diverges on one side is going to be controlled by the singularity on the right-hand side. And I won't go through the proof, which basically involves these writing everything in terms of Laplace transforms and proving that you can differentiate everything under the integral sign. So I won't go through that, except to show you that what you can prove is that another way of writing F, the deformed F, in terms of the undeformed F, is a kind of a Weierstrass integral transform with a kernel K, which is basically a Gaussian kernel multiplied by this integral, which is some kind of incomplete gamma function. But the main thing is it has a symmetry, and the delta goes to 1 over delta, and this symmetry implies our theorem. Okay, so one way that you can restore the symmetry under T is to use, yes, hello, is to use as a model the one-point function on a torus, and then you can show that if in the original theory, in the undeformed F transforms like not quite a modular form, but the modulus of a modular form, then the deformed version also. So you can also talk about deformed hemispheric characters, which actually transform in a different way, so that because the hair corresponds to taking a trace, and they have integer coefficients here in the characters and the multiplicities. You do not want that to change under the deformation. So there is a way of defining that. So as it all works out. So you can also apply it on the torus in general to products of characters, which of course is what appears when you compute the partition function on the torus. And you can show that the deformation of the products of characters is good, and it transforms in the right way, as you expect it would under a modular transformation of the torus. And the only interesting thing about this is that you can use the proof of this fact and apply it to all kinds of identities on deformed products of modular and Jacobi forms. And if you read, for example, a standard textbook on the subject, as we know, the Jacobi theta functions, quote, obey a bewildering number and variety of identities, and a lot of these identities turn out to be preserved by this T-Tbar deformation. So I'll conclude here by just mentioning a few consequences and questions. So what this T-Tbar deformation does basically is to generalize modular forms to functions with this irrational power spectrum, where the integer power spectrum gets replaced by these square roots. You can look at deformed modular identities, which give you interesting relations for arithmetic functions. For example, you know that the inverse of the Hagedorn eta function is the generating function for the number of partitions of an integer, and there is a deformed version of that that appears to lead you to interesting and possibly new relations involving P of n. Because you have these deformed theta functions, that suggests that they might be useful for constructing new and maybe integrable lattice models. And I should also mention that T-Tbar is just one of a whole family of, quote, of similarly solvable deformations, and it will be interesting to understand this. But I want to stress that a lot of this is just a generalization of mainly French early 19th century mathematical physics, which certainly underwent an incredible flowering in the early part of the 19th century, despite all the political uncertainties. And I think that our current generation, being led by people like Hubert, is managing to maybe reproduce, have a renaissance of what happened then, despite our political uncertainties now. So I'd like to end by wishing Hubert a happy birthday and giving him a little birthday present, which I should very briefly introduce. Hubert and I had a very, very nice email discussion when he was recovering early in the year, and we talked about the first time I met him in Paris and when he came to Santa Barbara, and how much he appreciated the landscape of Southern California. And we talked about art, and we talked about where he came from in Provence, and we talked about Cézanne. And so I would like to give him as a birthday present a very recent discovery, which is making a big splash in the art world, which is a recently discovered work, allegedly by Cézanne, when he came to Santa Barbara. And so with that, I would like to end and to once again regret that I'm not there. And I hope you all enjoy the rest of the conference. Thank you.
Well, thank you very much. Well, thank you very much, John, for this extremely elegant talk. Questions? You should say something.
Well, hello, John. This is Hubert. Thank you so much for the talk. And I should say you not only inspired my whole career, you also inspired the poster for the conference. I started thinking of Cézanne by looking at your paintings, of course, and you know I liked your Sainte Victoire à la manière de Cézanne, and then we thought, no, we can't have John's painting on the poster. It would be maybe a little bit too much, but thank you so much, John. So okay. I had a question about the Hagedorn singularity.
Yes.
Can you illustrate it a bit more for us? Tell us what it means in a context.
Yes, I didn't really explain that. Let me see if I have an equation which would show that. Yes, so it occurs if you're talking about a conformal field theory now, the smallest value of this delta is proportional to minus C, because it relates to the ground state energy. So if C is positive, which it usually is, then this value delta is negative. And you see there is going to be then, if you look at the n equals 0 term here, that's going to be the leading singularity. And if delta is negative, there's going to be a singularity here at delta equals, small delta is minus 1 over 4 pi alpha times large delta. Okay, and so there is going to be, basically, everything is going to be okay as long as this small delta is small enough. Now, if you recall what delta was, it was the ratio of R0 over R1. So if we fix R1 and we think about R0 as being the inverse temperature, if we have periodic boundary conditions in time, then R0 would be the inverse temperature. It tells us that there's a minimum value for the inverse temperature or a maximum value for that temperature, above which we get a singularity on the right-hand side of the equation, and that will correspond to a divergence on the left-hand side. And what basically happens is in a conformal theorem, field theory, AN is growing like the density of states in a conformal field theory. It's growing exponentially with the square root of n. And so only if delta is large enough is this series going to converge, because this has like e to the minus this. So basically, what happens is that when you get above this temperature, the effective density of states grows exponentially with n instead of exponentially with the square root of n, and that's the Hagedorn behavior. I hope that was a reasonable explanation.
Yeah, that's very clear and useful. All right. Well, thank you, John. See you soon, I hope. Bye-bye.
Okay, thank you.
Okay, we thank John again. And